Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RET 120 Hydraulics. Today we're going to have a discussion about pressure relief valves. And this is an incredibly important topic that we're going to constantly see and keep revisiting. And the reason why it is so important is because this deals with the safety of hydraulic systems and your safety. Okay, so a pressure relief valve. The whole purpose in its life, it limits the maximum working pressure to the system by providing an alternate flow path to the reservoir when oil flow in the circuit is blocked. Okay? So, I know that you're a little new to this right now, but let's follow through this basic hydraulic schematic, which I've drawn here. What I've got our pump pumping from the reservoir along a hose into a directional control valve which has a straight through position, a closed center, and a cross connect position to a hydraulic actuator, in this particular case, a cylinder. Okay, so in the straight through position, this one, pressurized flow is coming from the pump, going straight through to this end of the actuator, and it's filling up this cap end, pushing the piston face, and by extension the rod, out. What's happening on the other end is all this fluid in the rod end is being forced out, and again we're still in the straight through position, this one right here, to the reservoir. Makes sense. What happens to the flow when the cylinder has reached the limits of travel? Well, it's bottomed out. The cylinder, there's no place left for fluid to go. What happens is basically fluid pressure rises and rises and rises until some hose bursts. That is not an ideal situation. Additionally, notice our closed center position here. Even in a closed center, when we're in the center position of this directional control valve, there's nowhere for that fluid flow, the pressurized fluid flow, to go. It ends in a blind alley. So again, what happens? Pressurized fluid has nowhere to go, so pressure rises and rises and rises till something pops. That's why we put a pressure relief valve inside circuits. The pressure relief valve, I'm going to give you guys the schematic here. Again, as the name implies, it provides an alternate path for fluid flow from the pump to the reservoir when oil flow to the circuit is blocked. Again, it limits maximum working pressure. So that is our symbol for the pressure relief valve. I'm going to go over this in greater detail over here. We've got an in and an arrow passageway through and an out. I've got a spring that is variably adjusted, so I can change the value to whatever I want. And I've got a pilot port that is sensing pressure, in this particular case, on that inlet port. This is what's known as a normally closed valve. Okay, again, a pressure relief valve, normally closed, because as this arrow here implies, there is no passage from in to out or primary to secondary. or P to T as the case may be, pressure to tank or pump to tank. There is no passage in its normal unenergized state. However, when pressure on this pilot valve, the pilot passage increases to a certain point above what you've set here, the passageway opens and allows pressurized flow, an alternate path for pressurized flow from P to T. So that is a normally closed valve that has been activated. It opens, okay? So let's look at a very, 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 very simplified diagram of a pressure relief valve, known as a direct acting pressure relief valve. Okay, if you can imagine the valve body as a solid piece, and here I've got my manually adjustable thumb wheel, which is adjusting the spring pressure on this cylindrical shaped land that's blocking the passage from the inlet to the outlet. So basically I can't get around this thing because it's blocking the passageway. However, notice this pilot port here. I know there's pressurized fluid coming in this direction, but look at this pilot port. Pressurized fluid is directly acting on that valve. And if pressure exceeds what you've set right here, i.e. the spring pressure, what that's going to happen is the pressure is going to lift that valve off its seat. And allow pressurized fluid to flow from P to T. Okay, that is an incredibly simplified version of a direct acting pressure relief valve. One of the things to consider is what would happen if pressurized fluid leaked into this space behind us here? That wouldn't be good because, again, you would never be able to lift that valve off its seat because that pressurized fluid behind there is not going to compress. So what you'll often see is a drain passageway. And that's the same diagram with a drain passageway there. If fluid was ever leaked behind here, it could drain to the T port independently. And that's what's known as an internal drain. An drain line, if we remember right, is a dotted line, whereas our pilots are dashed, our working lines are straight solid lines. Why am I not showing an internal drain on here? Well, in the schematic, if it's got an internal drain, it's just the schematic, it implies that it has an internal drain if it's not there. However, if I externally drain this system, because some valves need to be externally drained, and we're going to go over which valves need to be externally drained, there would be this symbol here. The dotted symbol implies it is draining to the tank externally. It is not draining internally directly to this. Okay? So again, going back to our simplified diagram of a direct acting pressure relief valve, can anyone see the problem with this? The problem is namely this spring here. What if I wanted to limit my system working pressure to 200 psi? Yeah, I can find a spring for 200 psi. But can I find a spring for 5,000 psi? Yeah, it might work. And again, there's also the problem of the non-linearity of a spring. For a direct acting, I mean, think about this here. Here's pressure working on the bottom of this valve, pushing it up. Here's pressure from the spring pushing it down. There's going to be a point where that passageway is not all the way closed or open, and that valve could potentially leak things across, and it's pretty noisy, and that's what's known as the cracking pressure. The first pressure at which it opens. The initial pressure at which a pressure relief valve opens. This is in contrast to the working pressure, what you want the valve to work at. So let's say you've got a working pressure of 200 psi, your cracking pressure might be 120 psi. What's the difference between there? Well, there's a point where it's not entirely open and not entirely closed. That's what's known as the pressure override, that distance between. Okay, so that pressure override is a zone of nonlinearity that we'd like to avoid, and that's a major problem with a direct acting pressure relief valve. And this is in total contrast to the new device that I'm about to discuss, and that is a pilot actuated pressure relief valve. And I'm going to draw a new diagram for a pilot actuated pressure relief valve. So here's a cutaway diagram of a pilot operated pressure relief valve. And again, it still has the same purpose, to limit maximum working pressure in our system, but it solves the problem of the direct acting pressure relief valve where there is a requirement for a heavy spring and there's always the problems with a large pressure override. So a pilot operated pressure relief valve solves these problems by, here's our P port, here's our T port. It has, again, a valve that's closing the connection from P to T. So when it's closed, it's normally closed. Again, the same schematic. It still has the same schematic. P to T. It's normally closed. There's not normally a passageway. It's still adjustable. It's still sensing pressure from that side. What happens here is something neat. This valve has a hole drilled through it. And what happens is this pressurized flow can enter through here and goes back behind the valve. And if I was to draw what this valve looks like, here's this surface area on the top, here's the surface area on the bottom, and let's say that surface area is cut out of the bottom because we gotta do our valve seat. There's a little indentation on here. But what I'm saying is basically the pressure of both of these guys is the same and the area is the same because of that little hole there. And let's take out for the area for the little hole. Basically, the area on either side of that valve is the same, and it's going to hold itself shut because there's an incredibly light biasing spring that's forcing it down. So again, we got this light biasing spring that's holding it down. Basically, that's the only plus on it. So again, we're applying equal pressure to both sides, but the top has an ever bit so much more because of the light biasing spring right there. So you're asking, how does this work? Well, here's how it works. This is the dart, basically the pilot. This dart, this is where you adjust it. You adjust the pressure here. And now when pressure, because again, pressure acts pressure acts undiminished in all directions for a confined fluid according to Pascal's law. It's acting on the face of this dart right here. Now, when pressure exceeds the working pressure that you want it to work at, the relieving pressure, what happens is it pushes the dart off the seat and the dart goes back. What happens now? Well, all this fluid can go to the tank. What happens to fluid at that tank? It's incredibly low pressure. What was keeping our valve closed? Well, it was the balance of forces, the same pressure on the bottom and the same pressure on the top, added with a little bit of the bias ring. What happens if the pressure on the top is suddenly released, as in this case where the pilot dart pulls back? Well, the whole valve moves off its seat. And compresses that light biasing spring, allowing the full pressurized flow to come back, to dump from pressure to tank. And in this particular case, opening a passageway from P to T. Okay? So there's a number of things going on there all at once simultaneously. But the critical thing is a pilot operated pressure relief valve, its main portion, this main portion of the valve, is held down by the pressure balance on both sides because of the passageway in between. And once that pilot dart is unseated, the pressure balance is lost and the whole valve opens up. So what's neat about this here is the pressure override is incredibly small. Basically, all you have to do is overcome this slight light biasing spring pressure, because once the pressure behind that valve, i.e. on top of it, is removed, the whole valve completely opens up. Okay? So sometimes, because this is a pilot operated valve, it should actually be drawn like this, which is unnecessarily complicated. That is the true actual representation schematic symbol for the pilot operated pressure relief valve. And what you're seeing here, these dash dot SOS, it's an enclosure, and meaning this whole thing is actually one device. And what it's saying is, with this extra symbol here, that's the dart, which is acting kind of like a quasi-direct pressure relief valve, which is affecting this valve right here. People normally don't go to the extra time to write a symbol of this magnitude and complexity, because most pressure relief valves you find out there are pilot operated. So if you see this symbol, chances are it's a pilot operated pressure relief valve. Okay, let's go through the symbol again once more. Pressure, sensing pressure from upstream to tank. It's normally closed, indicating there is no passageway when it's unactivated state. And we've got a variably adjusted spring that in this particular case is internally drained. Okay, so after all this discussion about pressure relief valves, I know you know what the function of them is. It's again to limit maximum working pressures. What happens in a system with a pressure relief valve? Let's go back to the example of our simple system here, where we've got a pump hooked up with a pressure relief valve to a tank, a directional control valve, and our actuator, our cylinder. And let's say our cylinder is going to lift a certain load that requires a pressure of 100 psi. Okay, what is the system pressure going to be here when we are, let's say for example, lifting a load, or pushing the load in this case, in the straight through position? Well, basically what's going to happen immediately, as soon as it switched to the straight through position, this pressure gauge right here, that's the schematic symbol for pressure gauge. I should actually draw it a little neater. Is going to start rising and rising and rising until it meets the pressure requirements of 100 psi to lift the load. And then it's going to stay at 100 psi as that load is lifted. And then finally, the cylinder is going to bottom out. It's going to hit the end of it, reach the limits of its travel, and now pressure is going to rise and rise and rise until it reaches the setting that we set here for the pressure relief valve. And let's say we set it at 200 psi. So we went from 0 to 100, the load is lifted, it stays at 100 psi while the load is being lifted. The load reaches its limits of travel, and now pressure rises from 100 up to 200. And what happens? The pressure relief valve actuates, and that normally closed passage opens up, allowing pressurized flow to be diverted to the tank. And again, what is our maximum working pressure? 200 psi, and that is what our pressure gauge is going to read at this particular point, thereby limiting the maximum working pressure. Now, and again, I've kept it in the straight through position, and I can change it back to our closed center and retract it by going to our disconnect, excuse me, our cross connect, and that pressure gauge right there sorry about that, fix the drawing there. So that pressure gauge is again in our cross connect situation is going to be dumped in this particular case to the tank at low pressure. Okay, so again, the pressure relief valve did not change the pressure at which that cylinder extended. It did, however, limit the maximum working pressure. So let me ask you these following questions. What if the load requirement was 100 psi? We're going to keep it at 100 psi. And we limited our maximum working pressure to 400 psi. What would happen? Okay, cylinder goes, excuse me, directional control valve goes to the straight through position. The rod extends at 100 psi. Limits of travel are reached. Pressure would rise to 400 psi. A pressure relief valve would open, and maximum working pressure is limited at 400 psi. Exactly the same as we just did. Okay? Now, let me ask you this question. What if I limited my maximum working pressure to 40 psi? What would happen? Okay, same situation as we had before. I go ahead, switch my directional control valve to the straight through position, and pressurized flow enters my cap end, and pressure rises and rises and rises to 40 psi, and my pressure relief valve opens and dumping pressurized flow to the tank, thereby never allowing my system to reach the required 100 psi to lift that particular load. Okay, so what the point of this story is basically if you're having strength problems with your system, it is normally a pressure problem. And it could be a problem in the pressure relief valve is setting too low or opening too early. And we're going to go into the reasons why a pressure relief valve might open too early. I know this is hitting you like several tons of bricks here right now. You might have never had any exposure to these things, but trust me guys, we're going to be doing a lab on this exact same exercise we did right here, pressure relief valves, and this is going to come to you a lot stronger. Again, if you are having troubles with these things even after the lab, go ahead and review some of this lecture material, and by all means ask me questions. All right, that is it for the introduction to pressure relief valves. Yes, we're going to come back and visit these guys because they are very, very important.